Hello and welcome to this VJug session. Joining me is Oleg, and oh my God, we don't have another speaker. What's happening? Oh yeah, of course. In this session, Oleg is going to be our speaker. Welcome, Oleg. How are you doing?
I'm doing pretty well. Hi, everybody. Really excited to be here.
Yes, it's actually. I remember I gave a session to the Virtual Jug. I think when Thomas Romer he was going to do class leaders, and I think he was ill or something, so I gave that session. And this is now your first session to the VJug, and I think it's great that we have the organisers present so we can understand what goes great, what goes badly. So yeah, welcome. You're going to be talking. What are you going to be talking about today?
I'm gonna talk about concurrency, and we're gonna talk about different concurrency models in Java, or well, essentially on the JVM. So how people should think about that, how we can organize our mental picture, how different models drove from the bottom up. Well, basically concurrency in Java.
So this is an interesting one because obviously you're the head of Rebel Labs, right? So where did you start your concurrency journey? What was your route to creating this presentation?
Oh, and it's an interesting one. So yeah, before I started being a developer advocate, and I'll talk about this in a minute, I was actually a developer myself. So, and consequently, I was going lower and lower into the guts of the JVM, and then I worked at Zero for several years on the project that heavily involved Java agents and operating deep down in JVM. So obviously the performance and parallelization was a big topic there. So I started looking for things. And then at some point of time, I wrote a blog post with a similar title, Flavors of Concurrency in Java, which basically touched on the subject and which laid the foundation of this talk. And then I converted that when I realized that people actually are really interested in this. And well, here we are.
Yeah, so always a great way to make presentations actually by doing a blog post first, understanding it, and that almost creates the structure for the presentation. So that's cool. And of course, obviously, Oleg, you can't interview yourself. That would be crazy. So at the end of this session, I'll interview you, and I'll also do the write-up for this session. So this is actually going to go full circle, and we're going to create a blog from what was originally a blog. And okay, that'll be awesome. So. It does. Right, before we go any further, let me just share my screen so everyone online can see, for those of you who haven't used the VJug before. I can show you how you can pay for this session. Not pay for this session, sorry. Make your contributions. No, I'm joking. For those of you who haven't seen, this is the Virtual Java user group. You can watch this session either through YouTube or directly on our site, virtualjug.com. And today's session is going to be flavors of concurrency in Java. Our speaker today, Oleg Shelehev. You can follow Oleg on Twitter at SHELAJEV at Shelehev. The Virtual Jug is sponsored by Zero Turnaround and media partner of Rebel Labs. So after every single session, you will be able to see write-ups and also exclusive interviews with speakers on the Rebel Labs site. A little bit about Zero Turnaround. It's a company that create revolutionary developer tools based around productivity. So we have JRebel and XRebel. JRebel is a tool that allows you to view your code changes instantly in your running JVM. And XRebel allows you to profile your Java applications, your web applications at development time and make your changes instantly by integrating with JRebel. So do feel free to go to zeroturnaround.com and check out those tools as free 14-day fully featured trials. For this session, you can integrate with IRC directly using the Freenode, whatever it is, server and channel #virtualjug. And you can also share this group or session. Please do tell all your friends about this. Please tweet about it, Facebook about it. In fact, while you're watching it now, feel free just to go on Twitter and say, you know, I'm watching this session, and provide the link to the Virtual Jug site. If you have any feedback, as ever, at Virtual Jug on Twitter or directly to myself at SJMaple, please let me know what your thoughts are. Also, for those of you who are watching, if you are at any time upset with the video quality, there's a little cog at the bottom right of this YouTube embed. You can click on that and you can select your video quality, so you can increase that up to 720p or whatever your current network speed will allow. So without further ado, I think I've pretty much covered everything. If you have any questions for Oleg, please feel free to ask them in the chat and in the IRC chat, and I will ask Oleg directly. Oleg, would you like them during the session or at the end?
Well, generally, I'd like them more at the end of the presentation.
Okay.
But then again, I respect your judgment. So if you see a good question, basically that we will hop from one model of organizing concurrency to another. So after that, you can quickly ask a question that would be appropriate.
Okay, wonderful. So yeah, any questions, please drop them into IRC. So without any further ado, Oleg, I'll pass over to you and tell us about concurrency.
Yeah, thanks, Simon. Hello, everyone. Once again, I'm new to this internet presentation mode, so I hope you can see my screen now. And here we go, the keynote. Can you see my screen, Simon?
I can see your screen, yeah.
Yeah, that's great. So welcome to the presentation called Flavors of Concurrency in Java. My name is Alex Live. You can find me on Twitter. I like to connect with people and chat with people about anything. So if you have any questions, you can drop them directly there. I work for Zero Turnaround, which is a company actually based in Estonia, doing developer tools for Java developers. And my role currently is a developer advocate, which means that I care deeply about the community, which means all of you people. And one of my main responsibilities is to curate the Rebel Labs content engine portal that we maintain at Zero Turnaround, where we try to publish really good technical and opinionated content. So just go visit it. I'll be happy to hear any feedback about that. So, and once again, Twitter is the next thing that I maintain. So just not to disappoint you, before becoming developer advocate, I was actual developer without the advocate suffix. So I did solve my fair share of concurrency bugs and deadlocks. So I do have an idea how hard can it be sometimes. Hopefully after the session, we'll realize there are many different ways to solve concurrency issues and to organize our code, and we'll all become smarter. So let's start with a simple question. Why do we care about parallelization of our code? Why do we care about efficient concurrent code? And why do we hear this presentation? So obviously, this session won't make your code bug-free, or it won't make you a god of parallel computation application software developer. So we care because it is really interesting. It makes us better developers, and it allows us to reason about more things and have some abstract model about how world we live in, basically the hardware and software on top of that operate. So there was a thing called Moore's Law, which said that every 2 years, I think the number of transistors in the CPUs is doubled, which means that every 2 years, our hardware is twice as fast as previously. So that means that we don't have to do anything, and our applications will be running faster and faster. Somewhere around this 2011 year, this thing actually changed, since they couldn't fit more transistors on every chip. And what they started doing, they started multiplying the cores, basically the number of CPUs that can still execute instructions, but it's not a single CPU. So developers needed to change the model and change the applications to actually make use of this parallelization capacity. And since developers are really interesting people. So we invented magnitude models how to do that. And during this presentation, I want to go through all of them, or like several of them, and explain the benefits and trade-offs that they offer you. Because as developers, we often go for the shiniest technology, and we just like this fancy cat. We need everything. We hear something on some session, or we saw Netflix doing this thing, and we are like, yeah, we need this. I want that. We should do this in our small startup. Well, obviously, Netflix's problems and Google's problems are not a typical consultancy shop problems or a small startup company. So we should be very aware of the trade-offs and what do we get ourselves into. So not just to go for the best silver bullet solution. So hopefully after this presentation, we'll understand better what options are there on the market and how to use them and when to use them the best. So to start, let's talk about this duality between concurrency and parallelism. There are two terms that often are used interchangeably. They mean a little bit different things. And this image here is by Joe Armstrong, who is the author of Erlang, the language which is really great, and it excels at parallel computations. So he knows many things about concurrency, and he put it this way. So on the bottom of the screen, you can see 2 queues to 2 coffee machines, and that represents the parallel computation. You see, the system is parallel if it can execute multiple operations simultaneously. So at the same time, 2 people can come to 2 coffee machines and grab the coffees. So on the image above, so the one that represents the concurrent computation, there are 2 queues, but a single coffee machine. So the only thing that happens in parallel that happens simultaneously is waiting. So waiting is an not an operation. So it's not a parallel system. However, this concurrent system is capable of executing multiple operations if some resources would be added. So there are 2 queues. There is a set of coffee machines, and currently the system is not parallel, but the overall architecture of this allows it to become parallel. So as soon as we add the second coffee machine, the system becomes parallel. So parallel system executes multiple operations simultaneously, and the concurrent system is capable of doing so. But we don't concern ourselves with if it actually does so or not. So if it's just possible to do that in simultaneously, we're good. We are concurrent. Do or do not our resources allow that? This is a different question. So a more vivid example of that would be represented by those 2 pictures. I'm a big fan of this Mad Max movie, The Fury Road. And also, there is the same duality. So it's a movie about car chases and fighting. So during the car chase, obviously multiple operations happen simultaneously. Every car chases the title character, Mad Max, and they all progress. They make progress all at the same time. That's the virtue of parallel system, parallel computation. However, when the actual fighting is happening, then obviously Mad Max cannot fight all of them at once. So the scenes interchange, and they're fighting with different groups of people at the time. So the system in general could be parallel, but there is only one Mad Max and only one screen. So while the fighting scenes are concurrent, they're not parallel. So now, hopefully, with this very vivid example, you will never confuse those 2 terms. And in this presentation, I will kind of slightly use them interchangeably, but I will try to preserve the original meaning of system being concurrent and parallel if they just capable of executing operations simultaneously, or if they actually do that. So concurrency. It's a really hard topic. There are very many blog posts and resources on that, and how you can program your system to utilize the full potential of the parallel hardware. And it's hard because it usually involves multiple entities progressing over time. Obviously, they should communicate between each other somehow, and that is done usually via the shared resources. So our human brains don't work with parallel computations that well. We really need to reason about systems. We need some linearizable chain of events. We need to say which event happened before others. And when there are multiple producers, multiple consumers that do write to the same memory, and then on top of that, the hardware or the just-in-time compiler can reorder our programs, then not surprisingly we get locks and deadlocks and stuff like that, which is not great. So we will try to solve this problem or abstract ways this problem and see how to deal with hard problem of managing shared resources with multiple entities progressing over them in our code. So in theory, parallel computation should be very easy. If you have enough resources, then every thread or every entity that wants to progress should be using the allocated resources to them and kind of organize itself in a very neat picture. So in theory, the parallel system is represented by those puppies, lovely creatures. In practice, however, this happens. So the system goes out of hand and it becomes a mess. And what we don't want to do, we don't want our system to become a mess. So here on this slide, we can see different models of organizing concurrent computation, parallel computations, starting with bare threads at the bottom. And then we'll go through all these models in the next 40 minutes and talk a little bit about trade-offs and how the upper levels are built on top of the lower levels, and what do they bring to the table. So we'll go through threads, organized threads, or thread pools and executors, forward-join framework on the JVM, and then we'll go into completable futures, talk a little bit about actors and how they simplify the code that should run in parallel. We'll touch on fibers, and obviously on top of that, there will be the software transactional memory, which is the unicorn of concurrent computations, not very often seen in real life practice. So as Simon has mentioned, the whole this session has started at some point of time when I wrote a blog post about those different models. And that included a short one-question survey, what people actually use in practice out of those models. And the results, well, I didn't get like that many responses, but the results were heavily in favor of executor and completion services and bare threads. So you can see back on this slide, you can see that the lower levels, more closer to hardware, were much more popular for people. So let's try to explain why and why not. So we, instead of like just going and explaining things and by hand waving and magic and buzzwords, we'll try to pose a small problem that we can solve using code, and we will look at the code examples and try to realize what does that mean and how it will look in a bigger, larger system. Well, hopefully none of us, how many of us, this is a question that I would usually ask the audience, but since I just realized that there is no audience, I will ask Simon. Simon, what do you think? How many, what percentage of our audience write hello world applications for a living?
Well, it depends. I guess Java trainers would probably write hello world applications for a living. But I'm guessing that virtually no one will ever use
exactly
basic stuff.
That's a very typical response. So thank you for that. Thank you for listening as well. I like that I do have an audience of one. So the problem we're gonna solve would be usually it it might be like a small part of your larger system. So what we're gonna solve, we're gonna query different search engines over the internet, and we will return the first result, like whatever engine is the fastest, we want to return that result back to the user. So in terms of code, that would look something like this. So I have a method, get first result, and it will get the query string, and it will get the list of URLs for different engines. And the contract for this method would be like return the fastest result. So all the rest, all other results could be discarded, could be stored somewhere, could still be querying, but we need the fastest result. Fairly simple program, and let's see how it goes. So we start with the bottom level of that hierarchy of our models, and that's obviously threads. Why do we need threads, and why do we actually care about threads? Is because that is the simplest model that represents hardware the best. So at hardware level, we have multiple CPUs that can execute instructions, right? On the operating system level, we have processes, which are instances of programs that are executed in isolation, right? They're independent, that can communicate through sockets or files or just memory. And in the JVM, to model that, we have threads, which are lightweight processes. They basically, what you want to think of it is multiple streams of control flow. They share the same process. They have access to the same shared memory. They do have some local program counter and stack and local variables, local memory, but they do communicate mostly through access to shared data. So if we want to solve our search engine query problem in code using threads, the code would look like this. So in the middle, in the for loop, what we do, we iterate over engines, and we just spawn a new thread from a runnable using this neat Java 8 syntax. And what we basically say, imagine we have this web services.url.get method, which will actually go and query the internet and give us the result sequentially, right? So one thread can just go and do that. So what we do in this method, we create a new thread, one thread for every engine, and we try to get this result, and we use the atomic reference to a string object to get the first result. So this result compare and set method will only put the result that we get from the internet if the original value of the result is null. So if no other threads come before this, the first one will be able to swap the result. All the rest will just see a non-null result and won't do compare. So what we do here, we do new thread, we call the start method. That will trigger the life cycle of the thread into action, and they will start executing the code of this runnable that we provided. And then, well, obviously we wait for some result to happen, and then we return that. So there are two things that this code does, and it does specify the unit of work in this runnable. What do we want to do? And it specifies how those different threads should communicate, because we do want the first result instead of any result. This brings us to the question, how should threads communicate? And how do we want to reason about that? So this brings us to the question of thread safety. And a piece of code is thread safe. It's a kind of very weird definition. A piece of code is thread safe. It is if it manipulates shared data in a way that execution by multiple threads at the same time of this piece of code is kind of similar to executing that piece of code in a single thread. So that means that basically nothing bad will happen or nothing bad could even happen if we execute code in multiple threads. So given that we need them to communicate to come back with a single result, we do have a problem with the shared mutable state. So shared means that multiple threads can have access to that. Mutable means that we do change the values of the result over time. So well, this poses a question: how to deal with thread safety and how to organize the shared data access. There are multiple ways. So the communication between threads can be done by using just plain objects and their fields. We can use the atomics package from Java util concurrent atomics, which will give us objects that do have atomic operations, meaning that they will be isolated. Usually we use the queues, or in extreme cases, a database to solve the communication problems. But in any case, what we want to do, we want to reason about threads. And for that, we need guarantees that our communication is safe. So most definitely, you will be using multiple threads and you will communicate through shared memory, and you will need guarantees about what values threads can see at given points of time. So there is thankfully a way to organize that, and there is documentation and specifications that say how threads do communicate and what guarantees the JVM provides to you. And this helpful cat here just pushes us towards the direction of the right answer. And that right answer is obviously the chapter 17.4, the memory model that specifies what values can threads see. It's really complex and non-trivial subject. It beats undefined behavior every single time when you do need to create cross-platform code, or even if you want to provide like a single platform code, but you want guarantees about what is happening in the program. So if the only takeaway from this presentation would be, oh, I should go and check out the JVM specification or the chapter on memory model about that, I would be happy. This would make my day. If you have better takeaways or more takeaways from the presentation, that would be excellent. So to sum up how we use threads, they model the takeaway about threads is that they model the hardware and the operating system way of doing concurrency really well. This is a very low-level concept. They do take resources, so if we spawn new threads for every single task that we want, we might run out of the resources, and then everything will crash. On top of that, all those threads require manual management, so you have to be really, really careful about organizing your code to use just bare threads. It's really easy to do like one-off task in the background. It's not really simple to build a larger system out of that. So if you are at the very bottom level, if you're doing library or something, or if you create a program for a single user and you just want to go into the background to compute something heavier, then threads might be a good answer for you. If you want to build a system that multiple engineers will modify and try to understand, then maybe this manual management will be too much of a burden for your team. So if you know what you're doing, just go with threads and be happy about it. It's the most basic solution to organize parallel computation, and be with it. But be aware that you will be taking resources, and you will have to take extra care about the code that you write, because the separation between the units of work, between the work that you want to do, that runnable in the example previously, and the communication between threads, that atomic reference local variable, they will be really close together in the code. So that might pose a challenge for you. So if you want to go one level higher, we will get into the, obviously, executors. Executors are on the JVM level, on the Java language level, executor is an interface. What it provides you, with means to execute a command, execute a chunk of code, which will be well isolated from the rest of your code. So it is backed by, obviously, since the only underlying model for that are threads, right? It is backed by a number of threads. It's usually, they are pooled, so you will have a group of them that are managed for you within the executor. And you have two flavors of that. You will have the plain executor, where you can just say, oh, please, somebody do this task. Please execute this runnable, and just forget about that. Or you will have a slightly more complicated variant of that is completion services, where not only you can say, oh, this is a chunk of work that I want you to do, but you will get some sort of result back. So the executor or the underlying implementation will take care of communicating with at least your main thread, the one that waits for the result. So on the code level, our search engine code would look like this. Let's go through this code line by line, or several lines by several lines. So first, we instantiate our thread pool, and we use the built-in executors class. And we say we want a thread pool which will have 4 threads, and we want an instance of executor completion service on top of that. So now somewhere in the system, some code will take care of spawning new threads, keeping references to them. And what we can do now with this executor service, we can submit work to that and just specify. We don't need to specify any communication, right? So where before we had this atomic reference field, we don't have anything. So we just say, oh, please, service, go and query this URL, and we're done with that, right? So we don't organize our code around the communication, but just specify the work, which is a much better way to do that than doing with bare threads. And at the end, we make use of the service being a completion service, and it has a contract that you can take items from that, and those items would be the finished work. So this code will instantiate the executor backed by a thread pool. It will submit into that executor as many tasks as we have engines in the parameter, and then we'll naturally and automatically get the first result back, which is much simpler version of the code. Imagine that this instantiation will happen somewhere in the background or in some utility class. Then your actual logic will be really simple and very focused on the task at hand. So and you don't have to configure anything, which is great. So executors would be my preferred way to probably organize this, solve this task at hand, and no doubt, no wonder it was the most preferred approach. However, we have to realize that there are trade-offs. So I recently heard somebody said somewhere, maybe on Twitter, that things in software are cheap only when somebody else paid for them before. So with executors, that means that we don't want to solve our configuration problems ourselves, but somebody else has to think about them. So we submit units of work, we submit tasks to the executor. They have to be put somewhere. Naturally, that would be a queue. Do we want to limit that queue size? How do we want to limit that queue size? What happens if the queue is full? Like, do we spawn new threads? Do we just say, oh, please, I cannot take more work? What do we do when we shut down everything? Do we cancel every task? Do we cancel running tasks? Those questions still remain, but they are one level deeper than your application code. So you are higher. So you can separate now the configuration and the communication between the entities that will run in parallel and the actual work code, which is great. So For executors, the takeaway would be following. It's very simple to configure. You can easily get the upper limit on the overhead and say that this is how much resources do I have, and I want to utilize those, but I don't want to go overboard with them. And basically what you do with using executors, you push the complexity of configuring this thing deeper, somewhere deeper in the code. Maybe that would be the most senior or accomplished engineer on the team, or maybe that would be done in a different task. But you separate concerns and you organize code in a much more readable way. So yay, executors. Now, on top of the threads and on top of the bounded threads, executors, JVM offers you a fork joint framework. Fork joint framework, it was created and it was written for Java 1.7, and it was heavily focused on executing recursive tasks. So a fork joint pool, there is a concept of fork joint pool. The main concept in the fork joint framework, it is the executor. You can still submit tasks to that, but the individual threads that will actually compute those tasks, they don't just go to this main queue to get the work, but they also can chunk this work appropriately. Well, with your help, obviously, they can chunk this work into smaller pieces of work and solve the task recursively. And on top of that, the workers and the threads that are not doing anything at the moment, they can go and help their buddies to do the work. So the work stealing will be involved. And it is actually a great idea, because, well, if some threads are just waiting and doing nothing, might as well go and help me or help other threads to solve the problem. So a fork joint framework would after that, in Java 1.8, was rewritten almost from scratch. There were like major changes to that, and it was rewritten to be not just good for recursive tasks, but for any tasks, right? So you can just throw a fork joint task and execute that in the background in asynchronous mode, or you can do that from within the tasks. So both models of recursive computation and just background computation were preserved, and the API is pretty straightforward. What is even better, and we can see that in this code, that the streams that are available from Java 8, right? Streams, when they parallelize themselves, they make use of the underlying fork joint pool, the common fork joint pool that is pre-configured by the JVM itself, trying to take advantage from the parallel resources of the underlying system in a way like JVM can, because, well, that's your container, right? It knows the most about the environment it runs in, so it can configure things maybe a bit better or smarter than an average application. So the code is here, the example of code is even easier than we saw before. So we don't have to instantiate any thread pools. We just say, okay, we want to take a stream of the engines, we want to parallelize that, and then we use the map function. So in the functional style, we specify the work that has to be done for every element in that stream, and the work is the same, basically query the URL and give us result. But we make use of the implicit parallelization and implicit concurrency, concurrent capacity of the system. And on top of that, we just say, okay, I just need any result, so find any method is appropriate here, and we get that result. So as you can see, there is absolutely nothing in this code that talks about how the parallel computation should happen. So all those pesky details and actually hard problems are abstracted away from you by this concept of streams and by the fork joint pool framework that lies beneath it. And worth it. So here's the catch. Don't write code like this. This is a bad example of the code. Like if you want to copy paste that, and if you have this exact problem that you need to solve to get solved right now, this is a bad example of code. Don't do this, and we'll just talk about this in a second. So what happens here is that not only we just specify what to do, but we also kind of implicitly say that, oh, we will query the internet, which is a really long-running operation. If a website is down, if Google is down, well, usually you have more concerning problems than this piece of code. But imagine one search engine is down, then the query could take, well, say the usual timeout is half a minute, right? So the query could take half a minute to complete, which means that one thread that sits in the thread pool that is used by the forejoin pool that is shared among the whole JVM, that thread will sit there and wait for the result for half a minute. While that might be totally okay for you or for your application, and here we can see, well, like it's not our fault that the internet is down. At the same time, we do block the parallel capacity of the JVM. We do block the forejoin pool that is shared among all the clients in the JVM. So if some other component of the system would like to use the parallel stream or would like to use the forejoin pool, the common forejoin pool, they will have fewer threads available to them. So their performance will suffer. So whatever you do, if you use forejoin pool or if you use parallel streams, then don't use blocking operations. Make sure that the operation is very quick, as quick as you possibly can make it, and it just in and out, then the forejoin pool will do wonders for you. If you block, then, well, suddenly you limit the capacity and limit your performance by a lot. And it can lead to deadlocks and all the other things as well. So there are means to hint that you will block and how to mitigate that, but it will make code less readable. So we won't go there right now. So don't write code like this. Write code like stream.parallel.map something, but don't do blocking calls from within that unit of work. The takeaways for the forejoin pool: it's really efficient, like really smart people have written the code, and it's battle tested, and it's used in like hundreds, millions of systems, and it's robust. So it comes pre-configured, so you can have forejoin pool.common and obtain the instance of that efficiently configured pool. It's really easy to use. It's really easy to get it wrong and make the overall performance of your JVM worse than it could be. So great solution, easy to get wrong. I think that covers that. Simon, are you still online? Am I still online?
We are both still online.
Yeah, good. We're both online. I'm just, it's a little bit weird experience talking to my monitor.
Well, now you've allowed me to interrupt you. I'll ask a question which we already have an answer for, really, but I think I'll ask it anyway. So everyone else not on IRC will get that. From Firefox NX, which Java library does which form of concurrency do reactive Java libraries use? Do they tend to use executors or fork join pools?
Reactive libraries.
Yeah. So
that's a good question. So let's shortly talk about that. There are many ways of doing that. Let's talk about a concrete one specific library, which is RxJava, which is the implementation of the reactive extensions API standard, right, for reactive streams. And I'm not sure I have an exact answer to that. Most definitely, they use just executors, and you can provide a thread pool that they will use to handle those streams. I don't think they use the forejoin pool by default. I mean,
Yeah.
forgery pool is an executor, so you can sneak it in, but how smart an action that would be is a different question.
Yeah, so Firefox NX did look on the RX Java reactive library repo on GitHub, and he says it uses executors, but it was good putting you on the spot anyway.
Yeah, good catch. Dodged it. So forgery pool came in Java 1.7, and then it was rewritten for any computation in Java 1.8. So I would expect that RX Java works well on the other older JVMs as well, and it might work on stuff like Android, and who knows what version of Java API, Java-like API. Not sure how to politically correctly say that they use. So probably they don't use forgery pools by default. But good that we have questions and people listen. So let's go into the next model. So now we covered the bottom 3 levels of our models, and we go into the next one. So that would be completable futures. This is code for that. So in Java 8, the class called completable future has appeared in the JDK. What it represents a result of the computation that happens somewhere in the future or in background. So by default, if we run code like this, and let's take a look at that one by one. So we just say that we want to stream our list of engines anyway, and apply for every element. We want to apply this chunk of code. So what we say, basically, we want to supply the work that we need to do in the synchronous mode and execute that somewhere in the background by whatever means are available to the JVM, and we return the result. After that, we will collect the results and get the first one. However, and I think the code on the previous slide actually breaks the contract on the return of the first result, but that's not the point here. So we abstract away in this code, we abstract away absolutely everything. The only thing that we actually do say is this supply async, which we basically just say that I want this piece of code to be executed in the background, and I don't care absolutely how do I want to use this. The best thing about the completable future, and why I would bring that as a separate model, is that we use types. So, and those types allow us to combine the functionality, combine the code that will operate on the results. So we chain the functions. We can obtain a completable future, and then we can then apply a function to the result of the previous computation. And we will have a chain of completable futures to which we can then apply functions, well, indefinitely, and they will be executed either synchronously or in the asynchronous model. So we use type to abstract away this notion of the backgroundness, this notion of using the parallel computation. By default, the completable future, say supply async, will use the forgery pool. So in a nutshell, this is not entirely a different model of organizing code, but from the software developer's perspective, you get one level higher. So instead of just specifying work in a list, you can specify many levels of works, many functions that will be sequentially applied to the results of the previous computations. So the completable futures care not about the parallelization of the task, but it cares more about how you organize the code to utilize that parallel capacity, which is great. Another model that is more about organizing code than actually making use of the parallel resources is obviously, I love this picture. It's all about wonderful actors. So it's the actor model. Actors are what actors are. They are very lightweight instances that can execute a piece of work. They communicate using immutable messages, and it's about message passing architecture of your concurrent code. So message passing was actually one of the main things when object-oriented programming was just the term was coined. It was more about message passing, and only later we bastardized that to be about encapsulation. So different entities will communicate by telling each other things that will be immutable. So after that, they won't be able to change that. And the whole communication will happen using immutable code, immutable structures. So that means that there will be no problems with shared mutable state, because there is no shared state and or mutable state, and everything that is shared that is mutable is local, and you won't have problems as you would have with threads. And you don't have to write that by hand. So you have frameworks that do provide you with actors. So one example is Akka, and the code example will look like this. So you just extend an actor class. Well, in this case, we'll go with untyped actor. And what it does, the thing that you specify is that when this actor gets a message, it can do something with this message. So in this particular example, it will go and query the URL, and then it will use the get sender API and just basically communicate the result back. So what you did here, you completely separate, as in previous example with completed feature, you separate the work that you want to do, and you utilize the existing framework of actors to run the code and say how do you react to different messages. So there are untyped actors which don't provide the result back, so you will have to explicitly do this get sender tell things to organize the communication between them, which might be not the best way to do that. You can have typed actors which allow you for better composability of your code. So not only you will be able to just pass messages back and forth between different actors, you will be able to specify code in a natural way and use the return values as you do in the code. And the framework will take care about the communication. So basically, a little bit like in the completable future example, where you would be able to chain the functions, the functionality, and the framework will make use of the parallelization. With actors, you can, the same way, just call the methods, and the framework will make sure that the messages are passed, the different threads are, different actors are executed, and the scheduling and everything happens by the framework. So it's a great way to build a system. What it provides you is two things. So you can multiplex like a boss. Since actor is not a thread, it's much more lightweight. It doesn't have this resource overhead a thread will have. So we can have like millions of actors in a single system. And the second thing is that since you communicate with actors by sending messages, you have the structure, you have the hierarchy of actors. Basically, one entity can tell others what to go and do. So what you get for free in that, you will get the supervision and the fault tolerance, right? If anything happens in a particular actor in the code, so say if this web services URL query doesn't work, this actor itself, this fetcher actor, doesn't have to deal with that failure. Instead, the one that was calling it can decide what to do with this exception or with this error. So you get supervision and fault tolerance for free. So here I should mention that basically last week we had a great virtual jack session by Jonas Bonner, the CTO of TypeSafe and the original author of Akka, and he gave a brilliant presentation on resilience and how to design systems to be resilient, to have increased fault tolerance and not just degrade their performance and their utility when exception to error happens, but bounce back to the fullest. So if you want to learn about actors, just go watch that presentation. It's on the Virtual Jog channel. I believe Simon can provide you with links in the RC and everywhere, and well, enjoy that. That's a really great presentation about actors and resilient software. So actors are much more lightweight than threads, and then we go into even more, say, advanced concept of fibers, which are lightweight threads. So one example that I know of this fiber model of computation is the framework called, or library called Quasar, which is maintained by people at Parallel Universe, really smart guys. What it does essentially, I won't show you the example of the code, but what it does, it introduces the continuations in your bytecode. So it takes the method that you want to parallelize and it inserts basically pauses or ability to suspend after every instruction inside that method. So instead of having longer chains of code that will be executed concurrently or in parallel and block a thread for a longer period of time, it will be able to pause that work at any given moment of time, like basically after every expression or statement, and then pass the control or pass the execution time to a different fiber. So it is a highly scalable system. It benefits, the ideal situation for that would be if you have like millions entities that will have to make progress all at the same time. So you won't be needing to switch between those heavy threads, but they will switch between themselves automatically using continuations. And the best part is that you don't have to do anything in your code. You just put an annotation on your method and say, okay, I want this to be like highly parallelizable. And when you have multiple entities, they will all happen to progress at the same time, because the work they do is much smaller. The units of work they do is much smaller. So the hour is up. Let's quickly talk about transactional memory, which is well, the top level in our list of models. So there are multiple frameworks that provide that. Transactional memory, in a nutshell, what it does, it allows you to treat the actual memory, the state, your runtime state in the JVM as a database. So what you can have multiple operations operating on memory. Say you have objects, you have mutable runtime state that is shared, but the operations that are not visible until you complete the transaction. So in the same way, all the operations in the transaction are either visible to all the outside threads or not visible at all, right? So in the same way, we would use, say, atomic reference in the example with threads. We would be able to write to different cells in memory and then commit the transaction, and those would be either visible or not. So this is a great concept. It would be extremely nice if that would work really well. I'm not sure how applicable the current implementation of the transactional memory and how performant they are. It is an area of current research. People offer different solutions. People write academic papers about how to organize this the best. I think the current understanding of that is that as long as everything goes well, right? As long as everything succeeds and there are no threads trying to observe the values in between, like while some transaction is happening, then everything is good. if you are, and the only thread that is changing the values in places, everything is good. You can optimistically write, you can avoid locking and everything, and it will be fast and shiny. However, when something fails, then you have a magnitude of choices what to do. You can retry the transaction, you can roll back the transaction. You will have questions. What does it mean for your code? How do you need to handle this failure? And basically what transaction memory is the ACID, the atomic, consistent, and isolated environment. It's not durable since it's in memory, so there is no durability at all. But it is memory that you can use atomically and in isolated ways. However, how practical that is, that's a question. If you have a great example where the transactional memory is used, I'd be happy to hear about that. So here we go, transactional memory, the unicorn. So just to sum up, we really quickly ran through all those models. So the bottom three levels, threads, organized threads, or thread pools, and the four-joint framework were more about the utilizing the parallel resources to the best of your ability. So you can parallelize your computation, you can bound the overhead, and you can use, in the four-joint pool example, you can use this parallelization ability to the fullest. The items on top were more about the organization of your code. So either using types or specifying lightweight entities to execute your code, or even just saying that, oh, I want this code parallelizable and really scalable. They were less about utilizing the resources and were more about organizing the code around the problem. And on top of that, the software transactional memory is just an umbrella. How do you call that? In the imperative way of organizing parallel computations in a really nice manner. So every problem will take care of themselves, and somebody else will pay for that in research, in the implementation complexity, and everything. So what I want you to think about this presentation is that we try to create the mental model of how concurrency works on the JVM, and what tools are available to us to organize this chaos on the left into this neat row of fluffy puppies on the right. So thinking about parallel computation in terms of those models, you might better understand trade-offs between them. So we had threads, which are just a quick takeaway. Threads were modeling the underlying hardware in the best way. Then we push the complexity of managing those threads deeper into the thread pool level, into the executors. Then we took care of utilizing empty or waiting idle threads to help the buddies in the four-joint framework. And then on top of that, we organized the code in a very readable way using completable futures or I don't know, parallel streams and the four-joint framework as well, actors of fibers. So this is what we did in this presentation, and hopefully you better understand those concepts now. So not to be just one-off presentation, I would like to recommend a couple of books what you can read if you are really interested in this topic. So one of them is 7 Concurrency Models in 7 Weeks, which is a great book. It doesn't promise you to teach anything in 21 days. So you might find it really useful. It talks about everything from the bottom, from the parallel architecture, about how threads and locks work, what is the functional way of organizing parallel computation. It talks about actors. It touches on subjects of data parallelism and how they want to organize your data, what data structures to use for better utilization by like parallel for parallel access. It's a great book. Hopefully you'll find it somewhere, maybe online, maybe in a bookstore. And the second book that I cannot recommend like enough, it's a classic book on the multiprocessor programming. It's on the Intel's recommended reading list, The Art of Multiprocessor Programming. What it does, this book tells an excellent story going from mutual exclusion principles and how to build locks and primitives for concurrent computation from the very basics. And it shows you the great examples of the code. The code is being actually in Java, so anyone hearing this presentation would be able to actually parse the examples and ponder about like what exactly why do you do this statement or that statement. And it goes from the mutual exclusion and concurrent objects to the foundations, how the shared memory is organized, to synchronization operations, to how to organize the consensus between threads, into spin locks, into monitors, into data structures for operations, how queues are implemented, what is the ABA problem. Just absolutely marvelous book. This is the second takeaway. If you read the memory model and consider reading this book, I would be really, really happy. So The Art of Multiprocessor Programming, go read it. Like, just put it on your to-read list and read it. So this is it. I'd be happy to answer any questions that we have currently, or if you have later questions, or if you're watching this video online, just ping me on Twitter and we can discuss this thing. And yeah, thanks for listening. It was fun.
Awesome. Thank you very much, Oleg, for that awesome session. We've got a bunch of questions which we're going to get through just very quickly. But if anyone does have any questions, please feel free to jump in onto IRC and ask your questions there. While you're asking those questions, I just need to go to Keynote. There we go. So this session, if you wanted to follow Oleg at Shalaev on Twitter. This session was Flavors of Concurrency in Java. Coming up, we have on the 6th of October, we have Java profiling from the ground up from Nitsan from Azul. He's going to be giving a session on the 6th of October. And then we have a session on generics, past, present, and future on that says 6th of October, but I think it's the 17th or something like that. But if you go to meetup.com/virtualjug, you'll be able to RSVP to them and join the virtual jug if you haven't already. And this session is via Richard Warburton and Raul Irma. Okay, so let me go back over to Oleg. I'll stop sharing my screen and we'll go to the first question. So we do have a bunch, so we're going to have to go through these pretty quick. So first question from Etormeirana. Sorry if I pronounced that wrong. Or what is the risk of an active system to deadlock?
That's a good question. So if you have malicious goals in mind, you can obviously make any system to deadlock. However, so imagine that we have like main thread, the main actor at the top, and then we send messages to workers, to different actors, and they will send messages further to split the work into smaller and smaller chunks. Imagine you will get a tree structure. As long as you don't have cycles, and as long as you in the structure, the possibility and probability of deadlocks are very small. So messages that are passed between the actors are immutable. So the data there won't change. So to read that, you won't need any synchronization on top of that, right? So you can just freely read that. So different actors and different, which will be executed on different threads, will not use the shared memory. and thus they won't need to synchronize the access to that memory on top of that. So the risk of deadlocking over those resources is really, really small. Well, there is no risk. It's all the mutable data, which is the reason for locking, will be within a single actor. So it will be the only one accessing that. So the probability of deadlocking is really, really small.
Cool. And also, while we're on actors, actually, I'll switch to Saver Flavor, who says, so actors allow you to scale over multiple JVMs. He does not mention this. Is that something particular to actors or not?
That's a good question. Yeah, of course. So those models, all of them are what we talked about, are within a single JVM process. So some models, some of them are easier parallelizable across multiple JVMs. Say actors communicate through immutable messages. You can easily send them through a socket or to a different JVM, right? And the chain of hierarchy, the hierarchy is preserved. Basically, you just get more resources from more parallelization capacity from different JVMs, from multiple JVMs, and you can utilize that really easily with actors. That would be much harder to achieve with trying to spawn one executor, one thread pool across multiple JVMs. So actors do shine at that.
Okay.
So yeah.
We have another question. Daquino85 says, is there a GitHub repo with a code example somewhere so they can try executing the different models? Is there anything like that available?
Yeah, there is no GitHub repository as far as I know. Your best resource would be the blog post on Rebel Labs, so zeroturner.com/Rebel Labs, or you can just Google flavors of concurrency in Java, or Simon will provide a link in the RC chat. And that post, there are actually 2 blog posts, the first one and the follow-up, with code examples, and you can run them and see how it works.
Awesome. And Saver Flavors a she. Sorry, I apologize for that. Other questions? Let's have a look. So, question from Marius Philippe. Question for Oleg. How scalable are fibers, given that there is no efficient way to swap thread stacks?
That's a great question. So the best resource to answer to those questions would be the say I know about like a single implementation of the fiber model thread on JVM. That would be the Quasar. So you can go into the GitHub repository. So they do not swap. So like basically you can go there and they probably have benchmarks. And I've seen really great talks and presentations online about fibers exclusively by people from parallel linears. So you can go to those resources. But in a nutshell, what they do not swap the whole thread stacks, but they instrument the code to basically you can to include every statement, say, in a continuation. So every statement becomes an individual chunk of work, and in the same way you can say an individual unit of work. So, and every thread, like the system that manages that, would be able to say, like, execute this statement, execute this next statement, and in between of those, it will be able to schedule different fibers to actually execute in the CPU. So it's extremely scalable. I've seen videos of some computer game with like millions of small spaceships. The whole business of those would be like just to try to figure out, do you want to fly forward, to turn, or shoot, right? So their work would be really tiny, and it could be executed really fast. But if you just want to swap, to create a thread for every one of them, you will obviously just exhaust the resources, and the context switching will be just too expensive for you. But with fibers, because they can just execute those 3 tiny instructions real fast, and then the task control to another fiber, they were all like flying smoothly within the process on a single JVM. Unfortunately, this is as much as I can provide on the how scalable those are. Actually, there are another. I don't want to just diminish the question, but there is an awesome presentation. Awesome presentation by the name "Scalable Means Awesome," and unfortunately, I don't remember the author. I tried to find the link and put it on Twitter. It talks exactly about the question in the form how scalable is X, and it really depends on your use case. So go watch the Fiber resources. Check out that presentation. Hopefully you'll like it. And this is my best utility here, just to point to things.
Yeah, a few people asking for specific Fiber style sessions as well, which sounds useful actually. So that would be very useful. Yeah, Marius does follow up actually saying there is no efficient way to swap thread stacks in the JVM, and the only method he's seen is to copy the stack in place, but that doesn't scale for deep stacks. Okay, one last question. I think we're running quite a lot over now, so a lot of questions. So one last question from Kedi, K-E-D-I. Are fibers akin to generator functions or async await kinds of things?
That is a very deep technical question, and I absolutely love that. I would say so. Don't take my word on this. I think they are more towards async await model. So I would think about the fiberized the code using fibers for the parallelization as multiple continuations, bounded continuations, and I would say that they can. You actually confused me with this question a lot. If I may, I would will just won't answer this now, and I will keep it in mind, and I will provide the result a little bit later, let's say on Twitter. So because I'm not sure, and I'm honest enough to say that I don't know this.
That's cool. Okay, so I think we're pretty much over now, so out of time. Thank you very much, Eddie. That was a really great session, very nice technical session. And what we'll do is we'll do a write-up, which may just be a copy and paste of your previous article on Rebel Labs, and that will provide some of the information that you were talking about. With those links to the books, and we'll grab those slides and make them available as well. This session will be available straight after on the Virtual Jug YouTube channel, and I'll also add it onto the virtualjug.com site. So thanks everyone for watching at home or work or on the train or bus or wherever you are. Our next session is on the 6th of October with Nitsan, and I hope to see many of you there. So thank you very much, and thanks, Oleg.
You're welcome. I had a great time this hour. So
great. Thanks. Bye.
Bye-bye.